Hi everyone, welcome to the numerical linear algebra. Today I would like to talk about the vector notation and definition and some properties of vector. This is the first lecture in the series of lecture I'm going to have about the linear algebra and the optimization. So let's talk about vector. Vector is nothing but the ordered finite list of numbers, right? So it should be ordered and then it should be finite, should have some dimension, n, m, 10, 20, right? They are represented usually as a column or row vector. In mathematical notation, or usually in a lot of textbooks related to the machine learning, related to the statistics, related to optimization, usually denote vector as a column vector. This one, the definition on the left, right? Which is when you stack the numbers vertically, right? Like vector A here. B is when you stack the numbers horizontally. It's a row vector. This is also used a lot when you actually write the code. So a lot of time people write the code in MATLAB for a lot of optimization or their application, they actually define it as a row vector, right? It's important to know that you can use whichever you like, and the difference between them is just a transpose. I'm going to talk about that. It's just important to match the dimension, and because you need the dimension matching for the multiplication and also the addition of the vectors. Okay, now let's talk about the special vectors. These are the vectors that are used widely in the literature. That's why they have a specific name. So unit vector. Unit vector is a vector that determines the direction of a vector. Right? It has a magnitude of 1. It only used to show the directionality. So, for example, here I have a unit vector for the Cartesian coordinate system, for the 2D Cartesian coordinate system in the red. So E1 is the first unit vector, usually denoted in the literature as I, and E2 is J, right? Now I have a definition of unit vector here, like EIJ. J is the position of a non-zero element. This is the position, determines the position of non-zero element. Position of non-zero element. And then EI is telling you which unit vector is you're actually choosing. So for example, E11, E1 means this one, or this one, whichever you want to choose. And then 1 means that the first coordinate, the first element. So it's defined as follows. EIJ is defined as follows. If I is equal to j, you have 1, otherwise you get 0, right? So for like EM or E10, let's say you have E10. What does it mean, E10? It means that 0, 0, 1, and then 0, 0 all the way. So this is the 10th position. So if j is equal to 10, then you have 1. Or if I equal to j, you have 1. If I is not equal to j, you get 0. That's how you define the unit vector. It's used extensively for a definition of a vector, for projection, and you'll see some application of that for definition of the linearity of the vectors. We'll talk about that in a future videos as well. Then zero vector. Zero vector is a vector in which all the elements is equal to 0. It's usually shown by the word letter 0. This is 0. Or in some textbooks, it's shown by 0n. It's an n-dimensional vector, meaning that this is 0n, right? So all elements is 0 and it's n by 1. It's a column vector n by 1. Or in a sense, row vector with n elements, 1 by n, right? So 1 vector, similar to 0 vector, now all elements is equal to 1. So the definition of 1n is here, is a column vector with all elements equal to 1. Sparsity is a very important concept, widely used in the real-world applications because it significantly reduces the amount of computation, time complexity, space complexity as well. It's a vector whose most of the elements is 0, or many of its elements is 0, right? So for example, this zero vector is the most sparse vector because all the elements is zero. And then right after the zero vector, the next sparse, I wrote it here, most sparse. The next sparse vector is a unit vector, right? Because there is only one non-zero element, okay? And what is the least sparse vector is a one vector because all the elements are non-zero, right? Okay. Now, for the sparse vector, there is a term used to define the number of flops, floating point operation, and the time complexity and space complexity is called NNZ, or n-dimensional vector X. It's defined as a number of non-zero elements because the zero elements do not contribute to the number of flops. So I will write it here. Zero elements do not contribute to the number of floating point operation. So we work with NNZ, number of non-zero elements. Okay, great. Now, what's the example of vectors in real-world application? So vectors used everywhere, pretty much. They're integrated part of linear algebra, and linear algebra has numerous applications everywhere. But they have also application besides linear algebra. For example, in probability, when you want to denote the multinomial distribution. Multinomial distribution is nothing but a discrete distribution, right? So I have a definition of multinomial. The vector p probability is defined as p1, p2, pn in such a way that, like an axiomal probability, the sum of this pi is equal to 1, and each pi is greater than or equal to 0. Right? So here, for example, I have an example of multinomial distribution with 3 elements. Each one is equal to 1/3. So they are all equal likely. You can stack them like a vector here, column vector that I have here in pink. That's one application of vector. The next application of vector is time series. So ordered value of some quantity indexed by time. It's very similar to the definition of vector. For example, here x1 can be the value of the quantity at time 1, x2 a value of another quantity, same quantity at time 2, and then xn at time n. You can stack them vertically as a column vector. Images, like in image processing, computer vision, when you have an m by n image is usually a matrix, or now considered like a table, 2D. Like it has a rows, it has a columns, right? So m by n image has m rows and n columns, right? Then you can stack them horizontally or vertically, however you like, as a vector, right? The number of elements should remain the same. If you have a column vector, you have only one column, therefore the number of rows should be m by n, right? Because the number of elements should be preserved. Now I have an example here. For example, if you have this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, let's say this is an image, right? What's a table? If you want to write it as a vector, just stack them vertically. 1, 2, 3, 4, 5, and all the way to 12. You don't have to stack them like that. You don't have to go row wise. You can go them column by column, actually, right? So for example, another valid representation is can be like 1, 5, 9, and then all the way to 12. That's also another valid representation. Like first you write the first column and then write the second column like that. Okay, now video. Video is a sequence of k images, right? We know how to convert the image to a vector, so therefore we know how to convert the video to an image. This is very important in a lot of modeling or a lot of application you model in real world. You actually convert it to the vector first, and then you convert it back to the image or video at the output. So how would you convert them a video to an image, right? Sorry, to an vector. Vector is 1D. I wrote it here 1D, right? You know that the number of elements should be preserved. We are not looking for any lossy transformation here right now. So the number of elements should be preserved. You have a column vector. So the number of column is 1, right? So the number of rows should be, you have k image, each one is m by n. Should be k times m by n, right? Okay, great. Now in machine learning, use excessively, like you to denote the feature of your data, right? Feature matrix we call that, right? So for example, here I have F1, F2, F3, F4. These are the features. You want to feed it to the regression model, to the classification, clustering, right? So each of these F1, F2 are like a column vector, right? Another application, let's say you are working with this graphical modeling. You want to model a student's understanding of subject. You are using HMM, it's some sort of algorithm, hidden Markov model, right? So you have a student's a test score. Like, for example, the first test, a student got 100, the second one 80, then 60, then 95, and then 50. You want to see what is the most likely sequence of hidden states. Like hidden states can be a student's mastery level corresponding to this test score. You feed this 180, 60, 95 as a vector, row or column, doesn't matter. And then you will see what's the sequence of most likely states. Used a lot in graphical modeling and machine learning. Good. Now let's talk about vector addition and subtraction. So when you define a vector A to be A1, A2, all the way to AN, and then vector B, B1, B2, all the way to Bn, right? So you define them general in terms of n components, right? When you add them, this means that you add them component-wise. So A plus B means that the first component of A is added to the first component of B. The second component of A is added to the second component of B, and then all the way to nth component of A added to the nth component of B. A minus B is the same thing. It's just you first negate B, you multiply by -1, and then you add them together, right? What will happen at the end is that you again subtract them component-wise. A1 minus B1, A2 minus B2, and all the way AN minus BN. Good. Now, it's always good to be able to visualize the summation and the subtraction geometrically or pictorially. It's better and you get a better idea about vector addition and subtraction in general. So this one, let's label them. This is vector, this is A plus B, let's put it. Addition, this is what addition is, right? So you start from tail up, so B, and then you draw a vector parallel to A. You start from tail of A, you draw a vector parallel to B, and then you connect it. You draw this long diagonal. So you get A plus B, right? For A minus B, right, you will do the same thing. You just follow the definition. A minus B is what? Is nothing. A minus B is nothing but A plus minus B. So if the vector B, if the vector B is this, then negative B is this. Same length, the same length. Magnitude is not changing. Only the directionality of vector is changing. Okay, good. So I have a vector B here, another color. I have a vector B here. This is the negative B, right? So I want to add A plus negative B. Well, we already know how to add the vectors, right? I start from the B, this B, and then I add this vector parallel to A. I do the same thing from the A. This is parallel to B, and then I connect these, right? So vectors, all that matters for vector is what? Directionality and the magnitude. Vector is defined by directionality and magnitude. It doesn't matter where you draw the vectors, right? So for example, this vector and this vector is the same. Now if I can try to make them, yeah, like that, right? Doesn't really matter. So you can actually go ahead and transform this pink vector all the way to here to get this one, right? Because we want to relate to A and B actually. So this is going to be A minus B. If you want to remember this one, A plus B is easy. But if you want to remember that, remember this. This is the A minus B, right? Do you see this minus sign? It's from here, from B to A. A minus B is the vector from B to A, actually, right? Like what I draw here. From B to A. Okay, good. So you don't actually go through all these formalities, negate one of them, inverse one of them, the directionality, and then sum them up together and then transform it to the actual location. So all you can do is just is the arrow from B to A. Okay, good. Now multiplication, I have to say multiplication by constant. Multiplication by constant. So C here is a constant and a scalar. By constant scalar, by a constant scalar. To be correct. So C is a scalar and it's constant. When you multiply them, you get CA1, CA2, all the way to CAN. What does it mean? You multiply this C, this constant C, scalar C, by each of the elements of the vector A, right? And of course, you can switch the place because C times A1 is equal to A1 times C, right? So in a sense, C times A2 is equal to A2 times C. And all the way C times AN is equal to AN times C. So this is equal to A1, A2, all the way to AN times C. So it's going to be this. Okay, good. Now linear combination. So this is a very important concept. Linear combination of an n-dimensional vector A and some scalars b1, b2, all the way to bn is defined. I can find the matching color, I guess. Yes, is defined as follows: as a dot product. What we're gonna get there, right? Is defined as a b1 a1 plus b2 a2 all the way to bn an. So you're gonna go and multiply the coefficient by the corresponding element of the vector, right? So b1 corresponds to the element a1, b2 corresponds to element a2, and then you just go ahead and multiply them and then add them up. Why do they call it linear combination? Combination is because you're combining these elements. Linear because you're just adding them, like a linear operation. So it's called linear combination. Now, it gets more interesting if you go ahead and replace this A, this vector A, by a unit vector, let's say AI by EI, right? Because you can do that, right? These are the vectors, and then you can go ahead and replace them by another vector, by EI is another vector, right? Then you can prove that any vector, any n-dimensional vector can be written as a linear combination of these unit vectors, right? Any vector, right? So this is linear combination of some vectors, a1, a2, an. They're all n-dimensional vectors, right? So this one I use an because I use an here, right? But if you go ahead and replace ai, right, the vector ai by ei, by unit vector, right? So then you can actually represent any vector in n dimension. You can expand that by linear combination of the unit vectors, right? Then, so here I'm going to talk about further about this spanning process. So let's say that A is a vector that you want to represent as a linear combination of the unit vectors, right? So first you write it like this. E1, we explain about that. E1 is this. To remind you, 1, 0, 0, 0. En is this. 0, 0, 0, 0, 1. Okay. So whatever the vector A is, you can represent it like this. And the components or the coefficients, like for example, Bi is equal to projection of A on the corresponding unit vector. This is not a really, it's a very easy concept to visualize. For example, I want to give you an example, right? For 2D, that is easier to visualize only because of that. So you have this vector. This is the vector that I have. What is the coordinate of this vector? Let's say 2, 2. Let's show it like this. 2, 2. Okay. So in order to find the x coordinate, here is called b1, beta 1. You're gonna go ahead and project that in this unit vector, e1, e2. What is the projection? I haven't discussed it yet, but it's like a dot product. But here, for example, is obviously equal to 2. So here bi is B1 is equal to projection of the vector here that I have A on E1. So it's going to be 2. And what is B2 is a projection of A on the unit vector E2, right? It's going to be again 2. It's a very important concept that you can represent any vector as a linear combination of the unit vectors. Well, you can represent any vector in terms of linear combination of the basis vectors, right? And we don't want to go through that, but the unit vectors are just basis vectors because they are first independent. Of course, they are orthogonal to each other, they're independent, and they can span the whole n-dimensional subspace. So it's not like that this choice of the basis is unique. You can have many different n-dimensional actually independent basis vectors, right? But regardless of that, the coefficients that you get should be the same. The B1, B2, they should be the same. Okay. But the unit vector is definitely the easiest one you can choose. This is another advantage of the unit vectors, right? Now let's talk about the inner product. Very important concept. The concept that I just talked about, the projection, is just the inner product, right? So inner product of two n-dimensional vectors means that, let's say this is A. It's good every so often and this is B, two n-dimensional vector, is also referred sometimes as a scalar product. Why is that a scalar product? Because when you do A dot B, you get a scalar at the end. You don't get a vector. It's called a scalar product. It's defined as follows. This is the notation usually used, the short form notation. C is a scalar, is defined as AI, BI. You multiply them component-wise and then you add them up, right? So for example, if I want to expand this, become A1, B1 plus A2, B2, the first component of A times the second component, the first component of B, the second component of A times the second component of B times A and B. In a vector notation, this can be written as follows: A transpose B, right? What is transpose? You swap the rows and columns, right? So here, A transpose becomes this, A1, A2, the column vector becomes row, and B1, B2, Bn, right? So when you multiply them, this one is going to be multiplied this one is going to multiply that, and then you add them up, right? So this is a very important definition. A transpose B is the same as sigma I from 1 to n, the length of a vector AI, Bi. Now, going back to this projection that we talked about, that this now A times EI, the unit vector, right? Let's see what does it give me. We know that we define A as this vector, n-dimensional vector. It's time to define EI as well. What is EI? EI is 0, 0, 0, 1, 0, 0, 0. What is this one? The ith position. Remember? When I equal to j, you get 1, right? So we just go ahead and multiply the component wise. A1 times EI1. A2 times EI2, right? EI2 is this one, for example. This is EI1, right? All the way AN times EIN, right? All of them are 0 because they're all 0. EI1 is 0, EI2 is 0. The only coordinate that is not 0 is the ith coordinate, right? So when you multiply that, you get AI times 1, and that's what you get AI. This is how you get the coefficient, right? When you actually write as a linear combination of the unit vector, that's how you can actually get the coefficient. Okay, you calculated this dot product. Okay, so now I have one example here. For example, I use three-dimensional vector. A is 1, 2, 3, and E2 is 0, 1, 0, right? The second coordinate is non-zero. The second element is non-zero. And then you just go ahead and multiply them together, and you get A2 equal to 2, right? This one is A2. Okay, if you want to get A3, what do? The third, you just multiply by E3. If you want to get the first A1, you just multiply by E1, right? Now there are some interesting things you can do with this dot product. For example, what if one of the vector is just one vector? We talk about these special vectors. Now, what if one of the vector is just one vector? Right, let's see what you get. Let's see what you get. This transpose this a1, a2, all the way to an. This multiply this, you get what? A1 plus a2 plus an. So if one of the vectors is one vector, regardless of whatever the other one is, you get the sum of the elements of the other vector, right? So it's very important to show it mathematically. As how do you show the sum of the elements of a vector? You just dot product it by one vector. Okay, good. Remember that. Another thing I want to talk about that is the expected value. Now, as in the context of an example of like a dot product. So we need to give you some definition. In the future videos, I have one video specifically about the expected value and the averages, this variance and stuff. But here I just, as an example of the dot product. So you define the expected value. Let's say that the x here is a discrete random variable. We don't really care about that. But for now, let's define the expected value like this. It's just an example here. E of x is defined as xi times probability of xi, right? Okay, great. So this p of xi can be represented as a vector. Remember the discrete random variable, the multinomial distribution, I talked about them as an application of a vector. This is just one vector. The first component is b1, the second one is b2, right? Good. So, and each bi is between 0 and 1. Because there are probabilities, right? And they should sum up to a 1, but we don't care about that. So E of x is equal to this. Perhaps it's good to write this one. Bi times xi. I just go ahead and replace the p of xi by bi, like this. Now you can write it as a dot product, right? You can write them as a dot product. This is a dot product of what? This is a dot product of b transpose times x. Right? Or, in a sense, what is b transpose times x? What is this? It's equal to bi xi, right? But this is the same as xi bi, right? 2 times 3 is the same as 3 times 2, right? Which is the same as x transpose b, right? Very good. The result is a scalar, x transpose b, and b transpose x is the same, are the same, right? Okay, good. Now here I'm talking about that if all the points are equal probable, then b is equal to 1 over n, 1 over n, and 1 over n. This is just a remark, which in another video I will talk about it extensively. What I mean by that, in the context of the vectors, this is in the context of a random variable. X is a random variable. But if you have it in the context of a vector, then you might consider all the points equal likely, right? Not random vector, just a vector, right? Then you will choose a weight of 1 over n for each one. And you define the expectation like that. We get them. It's just a remark. I have an example about the regression. Another example of a dot product you can use, regression. b1 x1 plus b2 x2 is similar to the linear combination, right? But in regression, usually it's good to have this one here. You have b naught plus as well. Doesn't really matter, right? Okay. So assume that, for example, x0 is 1. You can write b naught times x0, where x0 is 1, right? You can show this one also as a dot product. You can show it as follows: b transpose times x, where x is what? X is 1, x1, x2, all the way to xn. So this is n plus 1 dimension, right? Because we start from 0, and this is not b0, this is b beta transpose. And beta is what? Is beta 0, beta 1, all the way to beta n plus 1 dimensional vector. Okay? Another example of that, you can write it as it's like a linear combination, right? Now, I talk about that if x1, x2, x1 are the features, for example. This is for the regression, right? They are the features, and that's how you model a machine learning problem. Use a lot in the least score regression problems when you have a continuous features and continuous outcome as well, right? So it's just the application. Now, if you let x1 to be 1, for example, x2 to be t, and xn to be t to the n minus 1, then you have a case of, for example, curve fitting. In that case, you don't have like a beta naught because the already x1 is 1. So it plays a role of x naught. So when you have a curve fitting problem like that, what would you do? Let me rewrite that again. So in that case, we have y is equal to beta 1 plus beta 2 times t divided by x, but times beta n times t to the n minus 1, right? So in this case, if you want to write it as dot product, what would you get? You get beta times t, or let's use it the t like that, the capital T, for example. And you can define beta to be beta 1, beta 2, all the way to beta n, and t to be what? To be 1, t, all the way to t to the n minus 1. Okay, it's n-dimensional vectors. So these are all the examples that you can use dot product. In the next video, we will see that why dot product or this linear combination is so important. Special, we will see that in the next video. Let's talk about the flop counts. It's a very important concept that determines the complexity of your algorithm, right? The number of operations, floating point operations, because that's what is done inside the computer. It's determined a rough estimate, actually, not exactly, but a rough estimate of number of operations is done by flop counts. So it's important to have an idea how to calculate the flop counts for your algorithm. So we're going to talk about some basic examples here. So number of floating point operation, that's what the flop is actually. Flop stands for this, but it's a term that is widely used, right? So each multiplication, subtraction, and addition, they are just one flop, right? So for example, let's take a look at one example here. Example, x plus y, right? X is a vector, n-dimensional vector, y is an n-dimensional vector, right? It's good to define x like this, x1, x2, all the way to xn, y to be y1, y2, all the way to yn. So x plus y, we know that component points, we add them together. x1 1 plus y1, x2 plus y2, and all the way to xn plus yn. Well, look at this. Every component we have one addition only. One addition here, one addition here, one addition here, and one addition here. We have n addition. So the number of flops is n flops for x plus y. Okay, good. Make it slightly harder. X transpose y, dot product. We write it as a definition of xi times yi. I'm going to write some term to make it clear. x1, y1, x2, y2, all the way to xn, yn. Right? How many multiplication we have? N. We have one here, we have n term. One here, one here, one here, n term. N multiplication. How many addition we have? N minus 1, right? N minus 1. So we have n multiplication, n minus 1 addition. So we have 2n minus 1 flops. Good. So I said I show the rough number of operations to compute any expression, determines the complexity, the rough estimate of how complex is your model. Now, when you determine the complexity, you use this big O notation, like in the order of what's the complexity in the order of what. What's the order of your complexity, right? The order of, for example, n squared, n cubed, we have say log n, right? In that case, we can get rid of the constants. Doesn't really matter. When n gets large, the 2 or 3 do not really matter. So x plus y is the order of n. The number of is the order of n. Where is that? X plus y. Here. We have exactly n flops is the order of n. But what about x transpose y? It's O of 2n minus 1, okay? But it's again 2 of order of n, right? The 2 doesn't matter, negative 1 plus 1 doesn't really matter. So again, it's the order of big O of n, right? So the constants do not really matter. Okay, so we keep this one into the consideration as the lecture continues. I'm going to talk about the flop counts in the future videos, more challenging actually, when we talk about the norm and we talk about the RMS, the Pearson correlation. We calculate the flop counts for each one, and you will see that it's actually very easy. And it's based on these fundamental operations of subtraction, addition, and multiplication. So that's it for this video. Thank you so much for listening. See you guys all in the next video. Thanks.